Here's an example dealing with power and efficiency. We have a 1,720 kilogram car that's driving up a mountain, and it does it in 5 minutes. The vertical distance is 1,600 meters. The car's engine is 20% efficient, and we want to find out what the total power generated by the car is to get it up to the top of the hill. We can assume that the speed of the car is the same at the bottom as it is at the top of the mountain. What we want to basically do is figure out what the work required to get the car up to the top of the hill is, and see if we can go from there to figure out the total power required by the car. So so this is basically the conservation of energy problem. We want to get the work by a non-conservative force, the work by the engine, to get the car up the hill. So let's first start with a diagram. Here's the car going to the top of the hill. If we're going to apply the conservation of energy, then we want to mark the initial and final spots and put a coordinate scheme on here for the gravitational potential energy. So now let's write down the conservation of energy equation. We'll just write down the whole equation, but now recognize that not all of this applies. So we don't have a change in the kinetic energy per the statement in the problem, and we also don't have a spring. So those two terms don't apply to this problem. And then the other important thing to recognize here is the work in this equation by the non-conservative force, in other words, the work by the engine to get the car to the top of the hill. Would we call that the useful work, or would we call that the total work that the engine has to do to get the car to the top of the hill? In this equation, we can see that the change in the gravitational potential energy is equal to this work. What we're trying to do is get the car to the top of the hill. In other words, we're trying to give the car that amount of potential energy. So that is the useful work. That is what we're trying to accomplish. So in this equation, the work by the non-conservative force is the useful work by the engine. So now we can go ahead and write it that way, and also recognize that the change in the potential energy is mgy final minus mgy initial. And now looking at the coordinate scheme, we can recognize that y initial is 0. And so now solving that for the useful work and plugging in values, we find that the useful work is 2.70 times 10 to the 7 joules. So now we've found the useful work. Let's go ahead and underline that. And so now we can use the work to find out what the power is with the equation that power is equal to work divided by the time. Since this is the useful work, then that means we're calculating the useful power. So now we can go ahead and plug in values, and we find out that the useful power is 90,000 watts or 90 kilowatts. Now what we're trying to actually find for this problem is the total power, and so that's another significant number, and we'll underline that too. And now that we had the useful power, we can now use the efficiency to calculate what the total power is. So the percent efficiency is the useful power divided by the total times 100%. We can solve this for the total power, and then plugging in values, we find that the total power is 450,000 watts, or again, we can make that kilowatts, 450 kilowatts. All right, so that's the end of that example problem.